Notes from the end of class today, Wednesday, October 14th. Okay, so this was the example we were going through to find the moment on a beam that would cause the cracking to initiate in a concrete beam. This diagram right here reminds us that we have a maximum compression at the top of the beam down to zero stress at the neutral axis, this grey line, and then increasing tension all the way to the bottom of the beam. We define this Y bar here as the centroid of the shape, and we're going to get to that in a second. And we define YT as the location of the extreme fiber in tension, and it is by definition the overall height minus the Y bar. This diagram tells us that we have a maximum strain in the concrete tension at the bottom, a maximum strain in the concrete in compression at the top, and we can use this diagram to find the strain in the steel. Similarly, this diagram tells us the maximum tensile stress in the concrete at the bottom up to the maximum compressive stress in the concrete at the top, and we're note here that the stress in the steel is actually considerably higher than the stress in the adjacent concrete. So in order to solve this problem, we have to consider this area here of concrete and steel and find a way to find our properties of shape of that shape. And the reason that this is difficult is because it's made from two different materials. So what we do is we take an area equal to the original rectangle and add two imaginary areas of concrete to take account for the fact that over here we actually had steel. And so since the steel is n times stronger than concrete, we fill in one of the areas of steel with concrete, and n minus one of them are these imaginary wings of concrete that we're going to use to try and understand this shape and its behavior when it's under bending. So if we take an example here where we've been given a bunch of parameters, we've got the height, the width. You'll notice the width is a little bit less than half of the height. That's typical for a concrete beam. The depth to the steel, D, and again you'll notice that's about the height minus about 2 inches, and that's about typical too. Then we have an area of steel that's given, a strength of the steel. This is a typical number for strength of steel. A strength for concrete, also fairly typical. A strength of the concrete in tension, the elasticity of the concrete, the elasticity of the steel, and that allows us to compute N, which is that measure of how much stronger the steel is than the concrete, and we got N equal to 8 there. Okay, so we've got to go ahead and find out the properties of this shape when it comes to bending, and those properties are Y bar, the centroid, and I, uncracked transformed, also known as resistance to bending or second moment of area. So step one is to find the centroid. Centroid is the location of the neutral axis. It is where there's half material above the line and below the line, and we find it using the formula discussed in the previous video, which is a weighted average formula. This is it here. We do the sum of each area times its Y bar divided by the sum of the areas. And in this case, the green shape has an area of 25 by 10 and a Y bar of 12.5, which is just half the height of the rectangle measured from the top. The red shape has a total area of 16.45 inches squared, and it lives 23 inches from the top. So that's its Y bar divided by total area, and we get an overall Y bar for the shape of about 13.2 inches. I then go ahead and calculate the I for this shape. We have a formula for I for complex shapes. It is the I of the individual shape plus the area of that shape, the distance between the Y bar of the overall object and the Y bar of the shape squared. We do that for each shape. So for my green shape, I have an I of BH cubed divided by 12 plus area 10 by 25 times the distance between the overall Y bar 13.2 inches and the Y bar of the green shape 12.5 inches squared. For the red shape, I don't have any values for B and H because that red shape is fake and is really just there to stand in for the steel, but I do count its area times the distance between its centroid 23 and the overall centroid 13.2, you'll notice I flipped y bar I and y bar in this formula. It doesn't make any difference because you square the answer, so it doesn't matter whether the distance is negative or positive. So I plug all my numbers in, I calculate the answer, and I have an I uncracked transformed of 14,723 inches to the power of 4. Now, what am I going to do with that piece of information, both y bar and I uncracked transformed? I'm going to use it to find out what is the moment that would cause this situation here for the stress in the concrete in tension to equal F rupture, otherwise known as the tensile strength of the material. I know that strength of my material. I want to know what is happening in my beam when I've reached this point. I have a formula for this line. It is F equals my over I. And the specific instance of that formula here is that F rupture, the tensile capacity of concrete, is the moment that would crack it times the place where the cracking would happen divided by the resistance to bending. So in this case, I plug in all of those values and I get that the moment that would have caused this cracking was 592.6 kip inches. And if I understood the geometry of my beam, I could further back solve for the load on the beam that had caused that situation. Hopefully this helps you guys finish the homework. Do feel free to send me email if it does not.